Hi, everyone, and welcome to our usual Wednesday ITMP seminar. And today we are delighted to hear Gabriele Casagrande, who will report on his work with Emile Dudas, Guillaume Bassard, and um, sorry,
And Adrian Lotti.
Andrea Lotti, on the coupling of massive spin to field to supergravity. Gabriele.
Yes. So hello everyone, and let me immediately thank Sergey and all your department for the kind invitation and the opportunity to talk about my work. So as Sergey already said, I'm going to talk about this paper which we put forward at the end of February, and the title is "A Unique Coupling of the Massive Spin-2 Field to Supergravity." So I'll start by giving you a summary of the topics I will discuss and outline of the results. The main topic of the paper is the coupling of the massive spin-2 supermultiplet to pure supergravity in 4 dimension, n equal 1 supergravity in 4 dimension. And the main result of the paper is that this coupling is unique at leading order in the Planck mass, and the uniqueness can be proved just by requiring consistency with local supersymmetry. And as I said, this is the main result I'm going to discuss today. The tool which we use to prove this result is what is known as a supercurrent superfield, and I will give a review of what this is in supersymmetry and how we employ it to the case of massive spin-2 supermultiplet. I will then discuss some interesting properties of the coupling we find. The main feature is that it's a higher derivative for derivative coupling to the Riemann tensor, R mu sigma nu rho, and it has interesting connections with open string theory in particular. The last point I will touch is the relation to Kaluza-Klein theory, and what I mean by that will be clear towards the final part of the talk. So, as an introduction, I will let's review a little bit what is the massive spin-2 field and its role in supersymmetry. So, this massive spin-2 field is usually described by the free massive spin-2 field is described by the very famous fields Pauli-Lagrangian, which is characterized by the mass term who ensures the theory to be free of any ghost. The equations of motion that one derives from this Lagrangian have this form, which can then be reorganized in a standard Klein-Gordon equation for the field h mu nu, combined with these two constraints on the field. In minimal supersymmetry, the massive spin-2 field belongs to a multiplet together with 2 Majorana spin trial fields and 1 massive spin-1. And the supersymmetry transformations characterizing the free theory of this multiplet were worked out in these papers and have this form on shell and are such to leave a supersymmetric generalization of the fields Pauli-Lagrangian invariant. And this then contains modulo sum normalization, the fields Pauli sector we showed before, the Proca sector for the massive spin-1, and the Rarita-Schwinger sector for the Majorana gravitini, and all the fields satisfy similar, of course, supersymmetric equations of motion and constraint. So the goal we had in our paper was to study the couplings of this rigid supersymmetric multiplet to d equal 4 and equal 1 supergravity. And at leading order, this coupling is given by the stress energy tensor, so the coupling to the metric field, and the current of supersymmetry, which is the coupling to the gravitino. And in a supersymmetric theory, these two currents belong themselves to a supersymmetric multiplet, which is called supercurrent superfield. And so let's explain a bit more what this multiplet is. This multiplet, as I said, contains the currents of a supersymmetric theory. In particular, in addition to the supersymmetry current and the stress energy tensor, it contains an axial current as bottom component and some extra closure field, which depends on the specific formulation of the multiplet you're working with. It is a linear multiplet, so it's a real multiplet that satisfies this condition. And on top of this, it satisfies also a conservation-like equation of this form in superspace, where this C alpha is usually proportional to the traces of the currents and the field X. When working in this is in an object that can be defined in any supersymmetric theory, rigid and local, but in local supersymmetry, this multiplet contains the current of the gauge fields of supergravity and was used to define the off-shell formulation of supergravity, because essentially as the stress energy tensor and the supersymmetric current couple to the gravitino and the metric, one can define the auxiliary field of the multiplet based on the structure of the other current of the multiplet S mu. And this can be done in several ways. The first example of supercurrent that appeared in the literature appeared in the original paper of Ferrara and Zumino, and contains a non-conserved axial current as bottom component, and the field X is a complex scalar field. And the off-shell formulation of supergravity that can be defined starting from this multiplet is called old minimal formulation. Another possible multiplet instead is associated to a theory which possesses an R-symmetry, and so that the bottom component is the asymmetric current, which is now a conserved current, and the extra field one needs to close the multiplet is an antisymmetric field X mu nu, and the corresponding off-shell formulation of supergravity is referred to as nu minimal off-shell supergravity. These are two basic multiplets, but turns out that you're not always free to define them in a theory. So there's a more advanced formulation of supercurrent multiplets, which was provided by Komargotsky and Seiberg, which kinds of interpolates between the two. The multiplet is defined by this equation in superspace, and it defines a non-minimal off-shell formulation of supergravity. So we have our supersymmetric multiplet of the massive spin-2, and we want to study its coupling to supergravity. And to do so, we try to construct the supercurrent superfield associated to it to have a grip on the supersymmetric current and the stress energy tensor that one can define. So the starting point is to observe that the multiplet I showed you before possesses indeed an R-symmetry given by these general transformations, meaning that one can associate a conserved R-symmetric current to the multiplet just computing it from the standard Netzer method. Being this an R-symmetric current means that one can associate to the multiplet an R-symmetry supercurrent supermultiplet, as I was showing before, and the supersymmetry transformations of the supercurrent multiplet are these ones I've been displaying. And if one then starts from this J mu 0, this R-symmetric current for the massive spin-2 supermultiplet, and applies step by step these supersymmetry transformations, finds this stress energy tensor, which is made of 3 different pieces. T mu nu k is just the standard kinetic contribution that one expects from the free Lagrangian I was displaying at the beginning. But it also contains 2 additional terms, which are improvement terms, meaning that they are trivially conserved, and so that they do not modify the conserved currents of the stress energy tensor. And this is perfectly fine from the flat space point of view, but once the theory is coupled to gravity, improvement terms correspond to non-minimal couplings to the associated gauge field. So in this case, non-minimal couplings to the metric field. And the 2 improvements G and B have, though, are associated to 2 different types of non-minimal couplings. Because of the symmetry they carry, the G improvement can be seen to correspond to a non-minimal coupling to the Riemann tensor, while the B improvement instead is associated to a non-minimal coupling to the Levi-Civita connection. So while the first one is a perfectly good operator, you can write in a Lagrangian which is coupled to gravity, is perfectly different invariant. bare couplings to the Levi-Civita connection are not Diffie invariant, and they are simply not consistent with general covariance of a theory. And therefore, we conclude that because of the presence of these B-like non-minimal couplings, the supercurrent supermultiplet we constructed does not define a consistent coupling to gravity of the massive spin-2 supermultiplet. In order to look for instead consistent couplings, we need to modify, to move from this minimal starting setup and modify and study the other possible supercurrent supermultiplets that one can associate to this massive spin-2 supermultiplet. And in particular, what one can do is to add to the full supercurrent a multiplet of improvements. So a multiplet which improves all the current of the multiplet S mu nu. Schematically, it will act like this, in such a way that, hoping that such improvements are, one can define a good improvement that cancel the bad B1, leaving us with a perfectly consistent coupling to gravity. The possible improvements that one can write are of two types. The first is a linear superfield improvement, meaning that it satisfies the same defining condition as the original S mu 0 current, so this type of constraint. But one can also consider a more generic non-minimal improvement, so of the type of Komargovsky and Seiberg, which is associated with a non-conserved axial current. However, it's shown in their paper that this type of term can modify the stress energy tensor only with terms proportional to the Ricci scalar, meaning that one is never able to cancel the bad improvement with such non-minimal modification of the supercurrent superfield. Therefore, we start looking to the linear improvement, and one can use parity, the linear multiplet condition, and the requirement to not produce terms in the stress energy tensor with more than 4 derivatives to work out excuse me, an ansatz for the bottom component of this multiplet of improvements, delta J mu, which takes this rather simple form, which depends only on 3 coefficients, CB, associated to a bosonic term, and 2 CF1, CF2 coefficients associated to fermionic terms. And the idea is then to study the contribution to the stress energy tensor produced by this improvement to the axial current, and use the freedom given by the 3 coefficients CB, CF1, and CF2 to hopefully cancel the bad improvements and find a consistent coupling to gravity. We perform this analysis and we find that the improvement terms associated to to the coefficient CB and CF1 introduce new improvements of the B type, the bad type, and meaning that there's no choice but to not include them in the ansatz. On the other hand, the F2 improvement instead gives a contribution to the stress energy tensor which is exactly proportional to the bad one we found from the starting minimal setup. And therefore, we are left with only one single possibility to define a supercurrent superfield which corresponds to a well-defined coupling to gravity, meaning choosing to add this term CF2 with the right coefficient, and there is the associated stress energy tensor, which is the only stress energy tensor which is associated to a consistent coupling to gravity of the massive spin-2 field, takes this peculiar form, meaning again the kinetic standard term of the fields of the supermultiplet, together with a non-minimal coupling to the Riemann tensor, which is also higher derivative of the higher derivative type. So the uniqueness of this coupling has to be intended in this sense. Now that we find this coupling, we can go on and, sorry, I was forgetting to say that on top of this, one can also add non-minimal improvement terms of the type of Komargovsky-Seiberg, but one has, so there's a kind of unique class of couplings, but these terms can always be removed by a filter definition when working at 3-point. And so somehow the coupling at 3-point is unique in this sense.
Sorry, can I ask a
Yes,
couple of things?
please.
So probably I missed the first 2 minutes, so probably explain this. But what kind of a theory, let's say you forget about supersymmetry, like what kind of example you have in mind of the coupling of gravity to massive spin-2?
Well, there are plenty of possibilities, in principle.
Well, as far as I know, it's a bit tricky. Like there is the Riemann-Gebadadze-Torley theory, which is a massive spin-2. Then you can couple it to gravity. Then you have some kind of like bigravities.
Exactly. Yes, that's a Sandrosen
so
option.
you are planning to find some supersymmetric extension of this? No,
not really. We are more agnostic of that. Those theories are highly nonlinear and require, again, they depend on this nonlinear potential, which couples the two metrics, the massless and the massive one, in the case of the gravity theory. Here we are working at the linear level, so quadrating the massive fields, and we are simply asking the question: how many options are there that are consistent both with supersymmetry and general covariance, let's say.
Yeah, okay, but with massive spin-2, there has always been an issue that it's really hard to introduce interactions. There was this...
for the ghost theory problem, right? But to see the ghost, you need to have an understanding of the full nonlinear theory, I believe.
But I guess this can already be seen at the leading orders. So you introduce an interaction between spin-2 and gravity. So this is an interaction, it's a cubic vertex.
Yes, but on a flat background, if you want.
But I don't know, I think it can still break. To have a consistent massive spin-2 theory, you write a Lagrangian and it has some first class constraints resulting from it. So it's you have equation of motion that you can find one derivative consequence, zero derivative consequence of equations of motion. And this is important for having correct number of degrees of freedom.
Yes.
And once you change something, you can break all these features.
But I didn't change anything, because of the quadratic order, I'm not changing that part of the theory, right?
But let's say if you just start from massive gravity and you place partial derivatives with covariant derivatives, which I think is something close to what you are doing.
But then you for sure you have to worry about the problem of ghosts, right? In a non-trivial but I think that if you do what you were saying and but after introducing the covariant derivatives, you expand the theory on the Minkowski background and you restrict yourself to operators quadrating the massive field, I'm not sure you can probe the ghost part.
Let me try to figure out that, maybe. I mean, one thing we could do to check there is no ghost at this level is that everything can be written in terms of the Stückelberg field strengths, which have no ghost by construction. The thing that people don't want to do typically also, if you introduce coupling with the Stückelberg field strength, the risks you have is to introduce higher derivative coupling straight away, which cannot be simplified in the next way. Whereas when people try to extend theory of gravity, they want to have a large cutoff. So in this case, if we are not careful about that, we know that the cubic coupling is correct. But the other hint we will have eventually, which is not a check we did through the analysis of the ghost of the 3-point coupling, is that the coupling that Gabriele just presented is the one of open string coupling at 3 level in open string theory. So we also know that there is a nice extension of this to all nonlinear level, which will be provided by OpenString, but that's a posteriori.
Yeah, that is an example that works for sure. If you want, we could try to ask the question, are there other possibilities, right?
Okay. Then I also had another question concerning Levi-Civitas.
Yes.
So Levi-Civitas here and there. Does it mean that the theory is parity breaking? And why is that?
Well,
Or
well, I wouldn't care about parity breaking. I would care about general covariance breaking before, right? I'm not happy when I find this type of non-minimal couplings in my theory. And I'm trying to find those couplings which do not have this term in there. So for sure, if you have this problem, it's another problem that one needs to.
So, sorry, I think the question was about the Levi-Civita epsilon tensor, right?
Ah, sorry.
yes, yes.
No. By construction, everything is parity invariant.
But here you have the sum of terms, some of which contain Levi-Civitas, others don't. So I would assume that if you do some kind of reflections of space in space, then it's not covariant. Transforms not covariant.
Well, this function here has to transform as an axial current. Also, it transforms with a minus.
Okay, so it's axial current. Yeah, then it's fine. Yeah, it should be like that.
Yeah. So I was probably too fast. I'm saying when I said I'm using parity, I mean that I'm looking at this delta J mu, so the improvement to the axial current standing at the bottom of my current multiplet. And so in order to be consistent with that, you need to have something that transforms an axial current. So with in this case, with minus the parity operator.
Okay, thank you.
Thanks to you. Right. So I reached this point and I was saying that once we found this coupling, now I will discuss some interesting properties of this coupling. And one of these is we can study the 2x2 scattering amplitude of two massive spin-2 field mediated by gravity. There are some general facts about this kind of amplitude that were worked out in the literature. So the high energy limit of this kind of amplitudes, meaning for S large at fixed scattering angle in the center of mass frame, these amplitudes typically scale as S to the 5. And it has been shown that they can never scale in a better way than S cube. And this result has been shown to hold when the field mediating the scattering is a massless spin-2, massive spin-2 mode, or spin-1 or spin-0, so all the bosonic lower spin fields. The theories that have the best possible high energy scaling of the amplitude are precisely the massive gravity of the Ram-Gabadadze and Tolley and the Hassan-Rosenby gravity that were mentioned soon ago. Then instead, in the Regge limit of the amplitude, meaning for large S but at T fixed, again, the scaling of the amplitude cannot go lower. I mean, the scaling in S cannot be better than S cube. And again, this has been proven for all possible lower spin field exchange. In our case, we only have what we can probe is the amplitude mediated by a graviton, and the stress energy tensor is the that contributes to this amplitude as this form. This is the relevant sector of the non-minimal coupling I was showing you in the general form. And the resulting amplitude we find it scales as S to the 4, both in the high energy and the Regge limit. This means that, of course, we are in agreement with the literature on this, and this unique coupling has a better behavior than the generic S to the 5 scaling of these theories. However, as I was saying, one can always try to add this non-minimal Komarkovsky-Seiberg-like improvements, but if you do so, then you will worsen your amplitude, so that this specific coupling is also the best behaved in terms of the high energy scale of the amplitudes. Another interesting property of the unique coupling we find that was already anticipated by Guillaume is the fact that there's an interesting connection with superstring theory. In particular, this non-minimal coupling we find between the massive spin-2 field and gravity is exactly matching the one that can be worked out from the first open mode of the open string spectrum. So, I mean, this was very interesting. And furthermore, if we look at the Broca sector of the non-minimal coupling, we see that the theory contains this peculiar operator of the type Riemann FF. And this operator has been argued in the literature that it can lead to violations of causality that can only be resolved by introducing a tower of higher spin fields. And so these two, which tower of higher spin field that, of course, very much resembles the Regge towers that appear in string theory. And therefore, we claim somehow that this theory we have for the massive spin-2 coupled to gravity may provide some evidence in D equal 4 and with minimal supersymmetry for what is known as the string Lampos principle, so that somehow all the quantum theories of gravity can be realized as string theory. Right, so one at this point may complain and say that there is for sure another coupling. I've been saying that we find a coupling that is unique. One can complain that in principle there exists a second coupling that is allowed, which is the one that arises by compactifying a Kaluza-Klein some higher dimensional supergravity to 4 dimensions in a proper way. And this for sure does not carry any higher derivative. And indeed this is true. The multiplet I was showing before can be worked out also in this way, starting from pure supergravity in 5 dimensions and compactifying on an orbifold, which breaks the 5D n equal 2 supersymmetry to n equal 1 and gives in 4 dimensions a theory which has the supergravity multiplet coupled to a massless chiral multiplet and to a tower of massive spin-2 multiplets of the type we've been studying so far. And again, this for sure has no higher derivative, no minimal couplings at all of the type characterizing instead the coupling we find with our technique. And the subtlety is that once one performs this Kaluza-Klein reduction, the massive multiplet comes in what is known as the Stukelberg organization of the massive degrees of freedom. No? One can always use the Stukelberg trick to rewrite a massive gauge field in terms of these components of this type related by the Stukelberg symmetry. It's a kind of fake gauge invariance. No? And this is very natural in dimensional reductions because the Stukelberg symmetry are nothing but the massive mode of the original 5D gauge invariance. And indeed, that's what happens if you study this type of reduction. And the multiplet with which we started our analysis and which we used throughout all of it would correspond to the unitary gauge of the Stukelberg symmetry, which one can always use and corresponds to set the Stukelberg field to 0. Here I'm displaying the case of the massive spin-2 decomposition, but there is an analogous one for all other fields. However, there's a crucial point here in making use of the unitary gauge. And the crucial point is that you can show explicitly by studying that the reduction, this reduction I'm presenting of the 5D supergravity algebra, that imposing the unitary gauge has a strong implication on the supersymmetry transformations of your theory, because the requirement that the massive supersymmetry transformations are consistent with the unitary gauge implies that you must deform the supersymmetry transformations of the massless supergravity field with terms which are quadratic now in the massive ones. This is a non-trivial deformation which, of course, forbids you to, it's not compatible with the supercurrent or if you want, off-shell supergravity setup that we were using so far, because our analysis stands on the assumption that the relation among the currents of the supercurrent multiplet are the ones I displayed at the beginning, which are naturally associated to the undeformed of-shell supersymmetry transformations on the supergravity fields. But here we see from the dimensional reduction that the massless transformation must be modified if one wants to work with the unitary gauge, and therefore there's no way that the supercurrent superfield analysis we perform can capture this coupling. Which also means that the unique coupling that we find is a genuine additional coupling of the massive spin-2 supermultiplet to supergravity, or rather to undeformed supergravity. Next to it, we have the Kaluza-Klein coupling, which corresponds then to a coupling to the deformed supergravity multiplet. And we have this picture where we have one possibility given by the string oscillator-like multiplet, the one we worked out in the paper, and the Kaluza-Klein mode-like multiplet, which is the one I just described. The string oscillator one can be corresponds to a long multiplet in extended supersymmetry, while the Kaluza-Klein one can be seen to correspond to an alpha VPS short multiplet in extended supersymmetry. The string oscillator is defined by this unique coupling we worked out in our paper, which is unique in the sense I've been explaining. While the Kaluza-Klein mode, we don't have a proof yet of this, but the deformation that it implies is so specific that leads us to expect this deformation to be unique as well. The string oscillator also is associated to an higher, can be seen from this argument I was giving of the causality issue with the operator containing Riemann FF, is associated to an higher spin tower of fields becoming light when the mass of this of the massive spin-2 string oscillator multiplet goes to 0, which from this perspective can be related to the tensionless limit of a string theory, while on the Kaluza-Klein mode we have a massive spin-2 tower that becomes light for m going to 0, which is the Kaluza-Klein tower, and this corresponds of course to the decompactification limit instead. And so this picture where the massive spin-2 supermultiplet coupled to gravity is either embedded in a string-like configuration or in a dimensional reduction configuration is reminiscent of what is this infinite distance bargaining that appears in the context of the swampland program, when in the infinite distance limited moduli space you either get a string-like tower of fields or a Kaluza-Klein one. Right, so let me now go to the conclusion of this presentation and to give you some hints of what we would like to do in the future. As I said, the main result that we get in our paper is the fact that the coupling that there's a unique way to couple the massive spin-2 supermultiplet in 4 dimensions with minimal supersymmetry to, now we understand in what sense, undeformed supergravity. And this is our main result. It's a peculiar coupling. It's characterized by this non-minima coupling to the Riemann tensor and its higher derivative, but it can be done. In the future, what we would like to is, along the lines of the question that came at half of the talk, we would like to understand better the nonlinear structure that one can extrapolate from the coupling we find at leading order in the Planck mass, exactly to have a better understanding of the possible propagation of ghosts of the theory, as well as the causality violation issue, which is, again, not really proven. At the same time, we would like to check whether this unique nature also to even higher derivative extensions of the analysis we perform. One of the assumptions was that the resulting stress energy tensor was containing operators up to 4 derivatives, but the multiplet of improvements can be modified to include further terms, and this can modify the result. It would be interesting to get back again the uniqueness even at higher derivative orders. We would like to prove, as I said, that also the Kaluza-Klein deformation somehow is the the allowed deformation, or rather to disprove this statement in a constructive way. And finally, it would be also interesting to try to repeat the analysis we perform for a general higher spin supermultiplet, which I here write for a, if you want, where the top component is bosonic, but we think that the analysis we carry can be reproduced also in this more general case. And with this, I thank you all for your attention.
Thank you for your talk, Gabriele. Okay. Let's thank Gabriele.
Thanks.
Okay, questions?
Can I ask concerning like one of your last points?
Yes. I'll just move to this other. Yes, please.
Yeah, you said that you want to proceed with the Lagrangian. Do you expect to find a theory which would involve only massive spin-2 field and supergravity fields, or I would just assume that naturally expect that consistency of the theory requires all fields from string theory?
Yeah, that's.
Or you expect to find a closed sector which has only these two fields? Well,
so we have Lagrangians starting from the leading order coupling that this this multiplet that we find defines. You can write a Lagrangian, and you can, for example, start from that and extrapolate a covariantized version of the Lagrangian, for example, and try to study the consistency of that, the hints from the presence of this operator is that, as you said, such a theory is maybe not consistent on its own, and you need to modify it in a way that resembles string theory. Yes, but we don't have yet a proof of this statement. At the level we have, we cannot probe it properly.
Mm-hmm. But still, you like hope that it can be like potentially possible to find a theory which doesn't involve the complete, let's say, spectrum of string field theory, just massive spin-2. Because otherwise you are just essentially doing string field theory, right?
But bottom up, no? I have no notion of string theory from my construction. It's purely field theoretical, no?
Well, I mean precisely that you start from string theory and you try to rewrite it as a field theory.
But if you do so, at least that's what has been done in the literature. From the string amplitude method, let's say, you can write some couplings, and what we find is that just working in supergravity, we reproduce the same exact coupling. What you're asking, if I understand correctly, is that if we expect with this same field theoretical technique to kind of prove that you need the whole string tower for the theory to be consistent, right?
Yeah, probably if you go to higher orders, usually like more stringent consistency conditions occur when you go to higher orders in perturbation theory, when you consider like quartic vertices and so on.
Yes, but that's if you start adding these terms, you cannot use anymore the setup. Well, I mean, the tool that we use, you need to go, I don't know, like really old style, checking the supersymmetry of the Lagrange, and then becomes very, very hard, I would say.
Mm-hmm.
The power of the analysis is that we didn't rely on any Lagrangian at all.
Mm-hmm. And then another thing concerning this paper, I attended the talk, if I remember correctly, there was some discrepancies that they mentioned. I mean, this paper, Lust, Marco.
Discrepancy with?
They mentioned some discrepancy, if I remember correctly, between string field theory result.
It's not, if I may, it's not discrepancy with string theories, I find, is that their motivation actually was to match double gravity.
Mm-hmm.
So they were expecting to find like a coupling between massive and massless spin-2 fields, and they were hoping to get the same amplitude as you do find in B gravity. And what they did find is that by doing the sector of the open string, you don't get a matching, you get a different coupling, which is the one we have from supersymmetry. But so the discrepancy was well, it was not an inconsistency within string theory. It was just like their motivation was actually to have an example of a big gravity with a UV completion.
Yes. So this also adds, thanks, Guillaume, it adds also some something to the previous question. We're not trying to get a supersymmetric version of big gravity, and somehow these two discrepancies agree with each other in this direction, right?
Yeah.
And maybe what I think that I can add, which I forgot to mention in the conclusion, is that the same authors worked out also a similar analysis, but for the closed string spectrum. And it would be, but it's while here there's a one-to-one correspondence between their analysis and ours. In the closed string analysis, they have an amplitude which correspond to a mix between different multiplets involving a massive spin-2 field, and it would also be interesting to check that the proper closed string massive spin-2 supermultiplet gives the same result that we find in order to corroborate the uniqueness.
Okay, thank you.
Thanks.
I have a question. Hi. It probably kind of a relevant one. Suppose you consider supergravity with cosmological constants like gauge supergravity.
Yes.
What happens in this case?
I don't know, because we would have to couple it to you would need a curved background, and we had only a flat background in mind.
Yeah, so then you need to expand near anti-de Sitter.
Yes, but you need to start over, because the multiplet we started from is the free one in Minkowski space, and when you couple it to supergravity, if you respect this quadratic approximation, you can use the free flat equations of motion. If to do what you suggest, you need to modify the starting point from the beginning.
Yeah, but my guess would be there should be possible to generalize it to this case. But yeah, I don't know why, but maybe. Okay, thank you.
Thanks.
So a question from me about generalizing to high dimensions. So what do you think there will be, well, if we try to generalize for high Ds, do you think there will be a difference between odd and even dimensions, or the procedure should hopefully be more or less robust?
The procedure is, I don't see, I hope not naive, I don't see a problem in trying to use the same formalism. What may change is the constraining power. You may have more possibilities, and it's a question whether how much you can have a grip on them, because the peculiar feature of our analysis is that we could capture everything with in a rather analytical way. And if you start to increase dimension and to add more ingredients, for example, if you think about 5D, you have two gravities, so it starts to become more involved, then you may lose this power, and the computation may not only be more involved, but you can have less constraints, let's say, that help you with.
I disagree with you, Gabriele. The more you got, the more constrained it is, because everything reduced to 4 dimensions. If you have a coupling in 5, it will reduce to 4, and if you have only one in 4, for the minimum coupling.
Okay, but you can have higher, more supersymmetries, for example, and then you have different multiplets that you can consider. I don't know. Okay, maybe.
Yeah, but more supersymmetry is more constraining.
Sure. Okay, from this point of view, yes, but okay. Yeah, that's true.
Thanks. I see. Okay. If there are no more questions, okay, we're going once.
Okay, so it's not a question. I just wanted to make one comment. So probably you know that people now are interested in computing in relation to the black hole mergers to compute gravitational radiation, which is emitted. And because of that, people are interested in constructing interactions of massive spinning particles with gravity. And they prefer to do it by starting from field theory, from massive spinning field coupled to gravity, and then using some classical limit in which massive field, spinning field, gets replaced by essentially a black hole, a Kerr black hole. So I'm just saying that it seems to be somewhat related to what you're doing. So people are interested in coupling gravity to some massive spinning fields.
Thanks for the comment. I try to look into this topic because I don't know. I don't really know the subjects, but it's interesting if there's a way to apply this kind of coupling to a setup like the one you're mentioning.
Yeah, okay, this is just a comment.
Well, if I make comment on your comment, I mean, there are many work on that, but it's slightly different because, of course, they don't care about supersymmetry.
Yeah, sure.
And what they want is like an asymptotic of the higher spin. So they have this issue since they don't have supersymmetry. The non-minimal coupling that appear, they are not uniquely fixed a priori, but they have the way to fix it because they want to reproduce care. So there is some understanding of that, which is different from what we do. But the tool, there are crossovers in the sense that we be interested in what they get, they may be interested in
that's
like that. But it's a different question, and the physical question, which is very interesting, I think. It's really to have the asymptotic in spin, and what is the notion of non-minimal coupling, which reproduces the Kerr behavior.
Yeah, so this Kerr is non-minimal coupling, right? It's not.
Actually, they call it minimal, but in a way, it's there is a question of what do people call minimal or non-minimal for very high spin. But there is something which they call minimal, which corresponds to the fact that the 3-point function on complex momenta is as well behaved as it can at high energy, which differ from physical amplitude, actually. From the talk, I know it's not. I'm not an expert, but from what I understood, this is what seems to resemble Kerr.
Mm-hmm. Okay, thank you.
Okay, so we're going once. We're going twice. This is your last chance to ask a question. And okay, I think that's it. Thank you very much, Gabriele. Thank you very much.
Thanks to you all for your invitation. I apologize if I went probably too fast when I speaking. Okay, thanks for the interesting questions and for listening.
Yes, okay. Thank you, and hopefully we'll see you next time with new results soon.
Thanks.
Bye. Good luck.
Bye to everyone.